In this presentation, I will talk to you about a patent presenting logic encryption utilizing fault analysis, which patent filed on January 2013 by these inventors. Uh, as a general outline, this patent introduces a means of producing efficient logic encryption for circuits by utilizing fault analysis to find the best possible placement for the logic encryption circuit, the XOR and XNOR gates. The faulty result that's produced influences at least 50% of the output bits, which is the desired effect, and a path-based circuit is used to facilitate the key insertion, which is not just plain key insertion. Also, it's fair to notice that there's a lower area and power overhead compared to the conventional random insertion method, the previous one used. Now, fault analysis is a method of analyzing a circuit to determine fault propagation, how stacked faults are influencing the overall output. And to do that, this fault analysis produces the fault impact, a value that can determine the influence that I mentioned before of stacked faults to the overall outputs, and is shown here as a mathematical formula. Now, logic encryption based on this fault analysis is finding the gates with the highest fault impact that will produce the highest number of faulty output bits. The outputs of these gates are chosen, the output of the gates with the highest fault impact are chosen to be included in the logic encryption circuit. Two input XOR or XNOR gates with one input as a key bit, and the other input the output of the gate that we mentioned before. And this is summarized in this algorithm, which takes as an input a netlist and key size, and outputs the encrypted netlist. It runs for a number of key size, and for each gate computes fault impact and selects the gates with the highest fault impact and inserts XOR gates or XNOR gates at the end of them. This image shows a flowchart that pretty much summarizes the previously mentioned algorithm, and this is a comparison of with the existing logic encryption method, random insertion. We can see that the previous method, which is up the upper image, we can see that produces 0.5 Hamming distance, which is the desired effect, with a very high number of keys, which mean a very high number of gates, which mean much area and power overhead. While the presented method has this achieved this effect of 0.5 Hamming distance in with much lower number of keys. Now, in order to facilitate the key insertion, this patent introduces a logic encryption cell, which is a circuit to provide the key inputs to the XOR and XNOR gates. A path, a physically unclonable function, is the centerpiece of the circuit. The user is provided with two keys, a user key and a challenge for the path. The challenge is applied to the path to produce a unique, unpredictable but repeatable output, the response, the p-response. The p-response is used as a decryption key to an RSA decryption unit, and the user key, is used as an input ciphertext. So the produced decrypted plaintext, KD, is fed to the XOR and XNOR gate as key. The RSA, with this, the RSA unit prevents the user from determining the KD, the actual logic decryption key, from KD, from the keys user and bit challenge with which the user has. So, and with this method is highly resistive to collision attacks. Now, let's see how it compares with the Hamming distance, with the random insertion method as far as power and delay overhead. As we can see, these results are for the generic method, and they do not show that for 50% Hamming distance, the present method is much better. And the same thing can be said for the area overhead. If they were compared for the same area overhead, fault analysis method which will have a much less area overhead. And this is just an exemplary arrangement of how the presented patent will be used in a normal system.